We are Group 8, Client Eaton. This is our Gate 5.5 report. Our project aims to optimize DER systems by identifying the most efficient configuration based on user-defined goals, whether that's cost, emissions, or performance. We built an algorithm that tailors system recommendations based on those priorities while all staying aligned with Eaton's technical standards. We have 4 team members. Each one of us have different responsibilities during this project. As energy demand grows, traditional centralized systems are becoming less practical. Eaton is a global power management leader and is in a strong position to lead that shift toward distributed, sustainable energy solutions. DERs like solar, wind, and battery storage offer more flexibility, reliability, and reduce environmental impact. Our project helps simplify the complex processes of selecting the right DER setup, supporting smarter decisions and long-term energy resilience.
Like just previously said, there is an increased demand for sustainable energy and it has grown substantially within the past few years. DER safeguards energy to be used or stored in a proficient manner. And this project is mainly focused on manufacturing plants specifically owned by Eaton. For our scope of work and method, we started out with research and our initial design. And that made us construct our rough drafts. We built on those drafts and ideas to develop concepts. Then from those concepts, we finalized them and to a finished product. We use resources, as you can see to the right, like Python, Gurobi, GitHub VS Code, NREL, and tkinter.
This slide shows our initial rough draft of the graphical user interface. From the beginning, we envisioned there being sections for weighted objectives for variability and efficiency, as well as other user-defined input boxes for load demand, schematics, and other essential performance metrics. These early design choices helped carve our path for the DER optimization tool. So as we continue to refine our problem statement, we developed this second iteration of the GUI, which introduces more robust weighted objectives section that now includes quality, efficiency, cost, and environmental impact. We also added a dedicated section for site-specific data. This is our finalized GUI design. It retains many of the core elements from earlier drafts, but introduces key enhancements. We integrated a location input feature that fetches NREL weather data based on city coordinates. And we also changed the load demand section for clarity and functionality. And the weighted objectives now use interactive sliders for fine tuning. The DER configuration window is now more detailed, offering specific parameters tailored to each DER type, like name, size, lifespan, and efficiency.
So our final design description, the figure here shows our final design output using the previously demonstrated GUI. Our output breaks down our optimal configuration into configuration, how many PVs, how many turbines, what kind, cost, which shows you the levelized cost of energy for all of the components, as well as the total installation costs. And we've also included power, which shows you the annual PV, wind turbine, and grid energy, as well as the total renewable power production. Our output slide also shows 4 different charts: a monthly average power line graph, monthly power distribution bar graph, LCOE comparison bar graph, and a DER energy share pie graph. So our demonstration, we've used the following configurations. We used 3 different PV panels, 3 different wind turbines. We used an annual load shown right here. And we used 10 maximum turbines and 250 maximum PVs. Our results table here demonstrates the difference in having a lower renewable weight versus a lower cost weight and vice versa. So as you can see that as the weights change, your PV type is going to change, as well as your turbine type. The number of PVs stays relatively the same as the renewable weight goes down, as the cost doesn't shift that much. But you can see that the turbine numbers go down increasingly as the cost weight is increased. More important columns here are going to be your annual levelized costs, which you can see goes down as the cost weight goes up. as well as the total renewable generation, which you can see goes down as the renewable weight goes down. Comparison of these results, this is pretty much the table before, just in graphical form, so pretty easy to see that the objective weights manipulate the DR installation costs. As the cost goes up, you want a cheaper system. Same for the annual power generation. As the cost goes up and renewables go down, you're gonna have less renewable power. Finally, for our lessons learned from this project, we practiced data accuracy, learning where to get that data and how to prove that it is correct. Balancing weights was a huge challenge in our project, mainly with the renewable and cost objectives being so different. We had to levelize them in our optimization algorithm. Integrating every single program together, we ended with over 2,000 lines of code and 4 or 5 different modules for each function. So integrating everything together was a bit of a challenge, but we prevailed. And finally, our algorithm capabilities. Our team had no experience with mixed integer linear programming before we started, but we're all pretty well versed on it after working on this project for the past 2 semesters. Finally, our recommendations moving forward with this project is incorporating batteries and inverters to the final optimization algorithm. We think that it could be done relatively simply, but I think we think it would be a very good addition to the project. Packaging this as a standalone application, whether it's a web application or an EXE, we think it would be very good to have it not in just Python. Finally, adding power quality as a metric. So we have a third renewable cost and power quality weighted objective would increase the overall reliability of the system and improve the usability. Thank you for joining. That is all.